So, welcome to this evening session. A lot of people here, cool. My name is Jan Metzner, I'm a Specialist Solutions Architect for IoT with AWS. And welcome to this evening session about IoT and prediction. With me, we have later on Jens Greiner from SKF, who will tell us a little bit more about the real-world use cases that they have. So, what will we talk about in this session? If we talk about prediction and IoT, first thing is you need to sense data. You will see later on how we do that. The second thing is you need to do something meaningful out of the data. So just sending the data will not help. You need to do a little bit more. We'll talk about this one as well. Then, obviously, the talk covers machine learning. I will show a little bit, how to use Amazon machine learning to classify data. So to do even more than just what is the data, so just classify the data. I will do this in a live demo. I hope it works, so It can work, it cannot work. It just worked a few minutes ago, but we'll see that. And afterwards we have Jens, and he will tell you how this is done actually in a real-world scenario at SKF. So let's get started. Let's use a use case. One use case which we brought up is wind turbines. This is one of the wind turbines from Amazon. This is Jeff Bezos there. If you think about wind turbines, what is really interesting for prediction in terms of failure rates is actually the main gear. So if you look in there, there's a main gear, it's a planetary gear, and you can do something with attaching sensors there, because you can predict actually if the gear will fail at some point, or if it is already failing. If we come a little bit back, what does it mean? So in general, it means if I have a system, a machine, I need to detect different states. If it is failing, if it will fail, if it is totally broken. You, as a person, need to know this, You need to know the different states. It's not like we from Amazon will give you this, or our services will give this to you. You need to know what the machine is actually doing. You need to know actually how the machine is reacting, still you can do analytics and see something, but you need to know actually what's happening, What is happening if the frequency spectrum is different, At some point you need to send a technician and so on, so you need to know something there. And you need to know what data it produces, because just the data will not help you. You need to know what the data is. And we will look into this later on. So how do we do that? We have different services. So Amazon has all those building blocks. So let's dive deeper into two of those building blocks, which I will show today. The one thing is Amazon machine learning. The other one is AWS IoT. So let's dive into the little bit more complex one, I would say, for this talk, that is Amazon machine learning. So Amazon machine learning is a service where you just push your data in. We will create actually a model out of that, and you can do prediction with that. So how does it look like? We support three types of predictions. The first one is a binary classification, so just, this is yes or no. Second one is a multi-class classification, so I can detect a category from a list of items. And the third prediction is a regression, which means I can predict a numeric value, so how many sales will I have today. Amazon machine learning uses linear models. So there are a lot of different machine learning models. Amazon machine learning uses linear models, which means it can exactly do this. It can do a classification depending on linear weights of the data. And it can do a regression on top of this as well. To do the prediction, you have two types. You can do a batch prediction, which means you, for example, just have a lot of CSV files and just funnel this to Amazon Machine Learning, and you get a prediction for that. Or you can create a real-time endpoint and do real-time predictions on this endpoint, which means the model will react instantly, and you will see later on how instant this is. So there is some latency, but it's still real-time in terms of what we in the cloud see as real-time. You can tune the model, so I will show later on a little bit how the GUI looks like, but it's like that, so that you can tune the model a little bit in different directions, depending on the data and the data you know. Okay, so you need to know, okay, what is happening there and what is how many false positives, okay, and so on. So you can adjust this a little bit. On the training parameters, because you need to train the model with the training set of data that you have, there are different options to tune that. So one is the model size. Model size means, okay, how much RAM is used to do the prediction. Less RAM, obviously it's faster, but if you have too few RAM, obviously the prediction will not be as accurate. Second thing is number of passes for the training. So if you have a small data set, you can increase the number of passes to just increase the accuracy. But it doesn't mean that it will help all the time. So if you do that a lot and increase it a lot, it will not help. So you can adjust that. Next thing is data shuffling. So the algorithm goes sequentially over the data, which means in order to have a good model, you need to randomize and data shuffle just the rows a little bit to just have a more generic model that is not fitting just to this training set that you provided. And the fourth thing is the regularization. This is really important. So you can create a model that really fits your training data. That's the right thing. Okay, you see it fits exactly the training data that is there, but it will not fit any other data. It's not general enough to do predictions. If you see the left-hand side, it's too easy. Okay, so it will just, for some data it will work, for some other data it will not work. Okay, and you can adjust this, and something in the middle is what you want to have. A fitting that fits most of the use cases, that is general enough, so that is not only fitting your training data, but also the data that you are funneling later onto the model. Just be aware, obviously, you need to retrain the model. It's not like, okay, I'm building the model and then I'm done for 10 years. You need to retrain the model based on the data that you're gathering all the time. It doesn't need to be all the data, but at least you need to retrain the model. Now let's get to AWS IoT. AWS IoT is, I would say, the entry gate for IoT devices to AWS. So it holds the connection from a device to the cloud, to a broker. It holds a pub/sub mechanism, so I can send messages in and out. It can obviously scale to millions of devices easily. It does the security right for the devices, which means each device has its own authentication, so it has a certificate and a private key. AWS IoT manages this all for your devices, regardless how many you have. And it does also fine-grained permissions, so you can have a fine-grained authorization mechanism in order to do Internet of Things, which means you're connecting different things together, but only those things are allowed to talk to each other through the broker. Then obviously the heart is the broker that is just handling the message between different things and different participants. And then they have something like the rules engine. The rules engine itself can read data out of the broker, so it can match some parts of the data or all of the data and can react on those data. One thing the rules engine can do is actually it can look into the data. If it's JSON data, it can look into really the data and it can, for example, just react if certain values are true or not. It can reformat the data, but most importantly, this is actually the point where the integration to all the other services or parts of the other services which we have on our platform is done. So there are actions in there to call other AWS services. You see there's a bunch of services. Today we will concentrate actually on the machine learning part. So there's a direct integration to machine learning. So you can funnel data to machine learning and get a prediction back directly from the rules engine and can then, for example, do something with a prediction, send an alert. In the demo, you will just see it is republished on the broker to a different topic. But still, it is in the system, and you can just plug and play and add more services if needed. So let's look at an architecture. This is the architecture that you will see later on in the demo. If we go back to the use case, if it is a gear, and you want to measure actually the vibration. Vibration means you have a lot of data. Okay, so you need to measure a lot of data to really see, okay, what is happening there. You can try to funnel all the data to the cloud, but it probably doesn't make sense. What you need to do is actually you need to create something out of the data that is still meaningful and just use that to funnel to the cloud. And maybe you don't need to funnel all the data to the cloud and not all the time. So what I'm doing there, and which is very common, is I'm creating a spectrum out of the data. So you have frequency. And out of the just the amplitudes, you can do an FFT. And then you have actually the frequency spectrum, which means you know, okay, which frequencies appear in this period of time. And this is quite compressed. In this example, it's a little bit noisy. I will tell you later why, but in a real example, it's not that noisy. So it's compressed and it's very specific. And it doesn't mean that you need to send this all the time. So you can send this, for example, every hour or whatever. But it is, you can use that to detect, for example, has the system changed or not. So this is done here with AWS Greengrass. So our edge service, which is running on the device. Obviously, you can also do that in a normal device, but it's just some kind of business logic which is running on the device. And it's not running in the cloud, because as I mentioned before, it's not possible to funnel all the data to the cloud. Next thing is device gateway. So this is AWS IoT, the big box there. And you see the different topics where the data is coming in. Then you see a rule, an IoT rule, which matches and just archives the data. That is a bottom rule. It just archives the data, so I can do machine learning afterwards or do the initial learning with that and have a history of the data. And then you see the second rule, that's the one in the middle, where we do the prediction. So we have, as I said before, there's a direct path to Amazon Machine Learning. We do a prediction, and it comes back into the rule, and I can do something with the result. In this case, very easy. We just republish this on a different topic, but in a real scenario, you could run the Lambda function. You can do whatever you want, since we have so many integrations inside AWS IoT. Let's just do this live. And I will just show you what I have set up here. So I've made a small planetary gear, so similar to what you have seen in the windmill. So it is laser cutted, and since it's handmade, it's not as accurate as the stuff that SKF is building, but it's quite okay for the demo. I have different gears. So this one, you see it's okay, or you don't see that, but you will see in a second that this one is definitely not okay. Okay, you see there are broken teeth. This is an easy scenario, but it just shows you that you can really detect this. If you do that on a more accurate gear, it's even easier to detect because this one has a very noisy frequency spectrum. So before we start, actually, let's look how to train the data. The first thing what you need to do is you go to Amazon Machine Learning. Can you see that? Let me check, okay. And you funnel in data that you already gathered. You saw in the architecture I had data in through Firehose stored in S3. So I have already the data in S3. And I can just say, hey, please load this data. Next thing is, obviously, these are the different frequencies which are coming in. I will take all of those, and they are already marked. And more or less the last thing what I need to do is I need to define a target. So I've already classified the trainings data. So this is something that you need to do. You need to sit there and say, this gear is broken, and I have the data for this broken gear. So this is what I have in the CSV data as trainings data uploaded to S3. And this is just the target that I've selected. And then more or less, I'm just walking through this. And in the end, I'm selecting here the default recommendation. Otherwise, I could, as I've told before, I can adjust the model a little bit. And then in the end, I would just click here, create ML model. I will not do this now because it will take some time, but you see it's quite easy once you have the data and once you have classified the data initially for the training. Then the next thing is you go to AWS IoT. Let me just click here. So you go to AWS IoT, go to Act, you create a new rule there. This is a rule that is matching on different types of data that is coming through the broker. So I have already created a rule here. A rule itself is expressed in a SQL type language, which means you're selecting from a topic. You see here, I'm selecting from this topic. This is the input topic. And this is the integration to machine learning. So I'm calling a function which is called machine learning predict. This is a model I'm calling, and that's an IAM role that AWS IoT needs to assume to access and do the real-time prediction. And in the end, I'm doing an action which could be sending out an alert via SMS or funding this to Lambda, or in this case, just easily publish this back to the broker just on a different topic. So this is all I need to do. And then I can really try to see if I can do something with that. To make it more easy to see what's happening, just clear this a little bit. This is a test console. So you have a test console inside AWS IoT where you can just subscribe to certain topics and see what data is flowing through. You will not see all the data if there's too much data, but at least you see some of the data. The next thing what I did is, let me just find this one as well. I wrote a small script, which is also, it's just a website. It's connecting to AWS IoT from the outside, and it's just displaying the data that is coming in. So the frequencies that are coming in from the device will be just graphed here. So it's a small graph, and you see just the frequency spectrum as it comes in. So, and obviously the device itself, you see here it's a BeagleBone, but in the end it doesn't matter what kind of device it is. As I said, you need to do an FFT there, and you need to send the data to the cloud. So let's just start that quickly. So let's start with a good one. So it takes some time to do the frequency analysis. So this is done on the device itself. You see the frequency spectrum here. It's kind of noisy, yeah? But still it's there. And here you see, on the first thing here, you will see the data. So you see the data, how it is funneled to the cloud. And here you see actually the prediction result coming from the machine learning service itself. So this is republished there, and I'm just showing the complete result which you get. So you see what you get is here, you get the label because it's a classification, and you get actually the accuracy. You see 97%, but it will change because it's actually from the flight here, it's not as accurate as I trained the model at home, but still you see it's quite good. And it is changing, and it is predicted. It takes some time. It has some latency until the prediction comes back. But for this type of use case, it's totally fine to do that. It would be even okay sometimes to do that in a batch. But here we do that in real time inside AWS IoT. So what will happen actually if we just replace this? So again, this. Yeah, so now you see that or not? Okay, it's too late. It's 4 o'clock actually, European time. But yeah, so this one is really broken, and we'll just attach this. So the frequency spectrum looks similar. Yeah, is this not moving? Here we go. And you see, oh, shit. So you see, yeah, it's kind of broken. So it was easy to detect that. Obviously, in a real-world scenario, it's not as easy. Yes, it is. It's a little bit easier because the noise is not there. But you will have different gears and so on and so forth. So the world out there is much more complex. But you see, getting started to do that, it's definitely kind of easy. And you don't need to do that much to make that happen, okay? And from that part, actually, I would just hand over to Jens to see how this is actually done in a real-world scenario and how they use not only machine learning, but what it needs to be done to just do that. Okay, Jens.
Good.
Just come on.
Thanks. So, good evening. Yeah, pretty late. As Jan already mentioned, also for me, I'm also 9 hours ahead of the normal time. Good, so it's moving automatically. Okay, what is the next part of this session about? It's about 2 use cases I want to present. It's about a real use case to create a smart product out of an existing product. And the second use case is about fast analytics or analytics applied to a data set in a pretty fast way, data science project. So my name is Jens Greiner. I'm working for SKF as a manager for the IoT development team, which is a team that supports other teams within SKF globally and also external customer projects. SKF is a bearing or very well known as a bearing manufacturing company. It's a pretty old company, founded in 1907, so more than 100 years old, 110 years old now. And we have more than 44,000 people working in SKF globally, and we are distributed around the globe. So we are in more than 100 countries. We have manufacturing units, and we are nearly present in any country around the world with SKF people. When we look at SKF, we have defined 2 value propositions. One is for sure the product. So we're producing bearings, but also everything around the rotating equipment, how we call it. This means seals, lubrication systems. Sorry. And we are leading in this area. And the second value proposition is the rotating equipment performance. So, and this covers all services and solutions that helps our customers not just getting a good product from us, but also how to use the product on a daily basis to increase the efficiency. So if you have a bearing, for example, and you don't lubricate it as you should, the bearing will not last as long as calculated at the beginning. So the life cycle will be very short. If something unexpected happens, then for sure also the bearing will die pretty fast, maybe. So rotating equipment performance helps our customers to utilize the best or our products in the best way. When we talk about digitalization or digital business, we define this pretty simple slide. So on the bottom, we have our so-called asset layer. These are all the products we produce, the physical, tangible products we produce in SKF. So, and we all know, we talk about IoT, Internet of Things, so these products get more and more smart. That's something we are all talking about now since quite a while. On the other side, we have our customers, and the customers, they came up with more and more ideas, with more and more things and requests to us, and we want to deliver also new services to our customers. Maybe also services our customers are already not asking for, but we have some ideas what we want to do. But how to really connect this existing product, make a product smart, or develop new smart products and connect it to the user value, the smart services we want to deliver. And there's something in between, which is the so-called, we called it service layer, which is nothing else than we developed a digital platform that provides all kind of technology and services to really build rapid prototypes, test, and real products and services. And this digital platform, as you can see, we are using Amazon Web Services for the digital platform. It's about scalability, reliability, cost efficiency, security, all these kind of things. So, we saw a nice live demo about a gearbox, about wind turbines, we are monitoring. Predictive maintenance is nothing new. The technology changed over the last years, that you can do the things in a different way. We in SKF, we built condition monitoring systems more than 30 years ago. We built our own private cloud beginning of 2000. There was not the name cloud already existing, but it was just a need, if you think of these kind of wind turbines. So you need to bring the data somewhere in a central point where engineers could look at the data and analyze. But I will not go into the details. So what we have here, we have existing solutions for doing predictive maintenance, condition monitoring, analysis. So we have software tools since a long time in the market that fulfills exactly this use case or supports this use case. If it is wind turbines, vessels, ships, paper mills, whatever it is. But the problem is that we get more and more data sets we want to include. So it's not all about purely condition monitoring, it's more data coming up, and we don't know exactly what kind of data are put on our table and what kind of cool ideas our customers have or internal we in SKF have. So we get more unexpected data sets. And we have also customers, they add additional sensors to what we supply to the customer, our technology. They add new sensors. Also, these data need to be, however, integrated into the system for analytical purposes. So how can we do that? It's pretty simple. We get a question, we should deliver an answer to our customers, and in the middle we need some magic that happens. What we have worked on is that to get this data into an analytic or into something that we can analyze the data across all the different data sets, we started to develop this digital platform. This means we have a data lake, we have connectors to the different data sources, we can apply nearly any kind of analytics, and this will end up then in two different things. One is the decision. That gives you just a clear, like we saw in the example, machine learning takes you to a decision, good or bad, exchange, run, stop. These are clear messages. Insights is more the data science approach that you really look into, okay, what does it mean? Why does this happen? Because to detect the defect is nice, but it's better to prevent the defect by understand what is the cause of the defect. So these are two different ways of looking into the data. So you need different technologies and capabilities to analyze the data. Let's start with the first real use case. It's about how to generate in a fast way a smart product based on an existing one. So in this example, I talk about an actuator. It's an SKF product. You can see it on the bottom left here. It's a physical product. It's like a hydraulic cylinder, but it's not driven by hydraulic. It's driven by an electric motor. So you can very precise position this system. You can really exactly define what power, what force you want to have in the system. And this physical system is a system that we sell and we have services to it. And that's the physical layer. But we want to add a digital layer on top of that. And when we talk about a digital layer, this allows us to create additional services or also digital products. And therefore, we need to connect this product and to the cloud or to a backend system. In this use case, we have here a surgical table. And the surgical table has 4, it could be also more, depends on the type, has 4 actuators inside. And each of these actuators are connected to a so-called single control unit, and that's just an electronic device that steers the motors and controls the motors. So this is this unit. And if you're in the medical area, you're not allowed to just change the electronics, so everything is certified. If you change something inside, you need to certify again. Our goal was to be very fast in really building a prototype, a solution that we can use to go to our customers and ask if this is the things they really want, they like, and build a real product and service out of it. So we decided to build an external small device ROP, it's not the final name, but currently it's still called ROP. ROP for Read Out Box, yeah, because it's just something that connects to the central steering unit, single control unit, and has GSM included, GSM network capabilities, Bluetooth, RFID, and Wi-Fi. Wi-Fi is missing on the picture, but that's just a given thing. So we have all this typical communication, wireless communication possibilities. And there are a number of use cases we defined. I will talk about 2 different use cases. If you look at the left side, you see the OEM use case. And this is a digital product, which is the traceability. So for compliance reasons, they put 4 of our actuators into a surgical table. And for compliance reasons or for troubleshooting reasons, they need to know where the different components are assembled in which surgical table and where the surgical table is really ending up in which hospital. And that's not that easy today. But with this solution, the RFID tags identify the actuator to the ROP. This is pushed into the cloud, so we know exactly which actuator is mounted in which surgical table, and we can easily trace that. This is a digital product for our OEMs. That's a typical, pretty simple thing. On the right side, it's the big data. So we design our products for something we expect or we assume how they are being used in the field. But that's experience and assumptions, but it's not reality. Because think of this surgical table, maybe you have 4 actuators. This does not mean that all the 4 exactly behave or are used in the same way. Why should they last in the same, or have the same time or life cycle, how long they last in the application. So the big data gives us the possibility to throw all the data in about the usage of the actuators, to learn out of this data and use this for designing better products exactly for this kind of purpose. Also to identify failures, machine learning, and these kind of things to really help our customers to be more efficient in a design phase, but also in an operational phase later on. And there are other use cases too. When we talk about a prototype, so this idea was born in June this year. And we decided, okay, let's go for rapid prototyping to build really a connected product, have the data in the cloud, visualized, accessible, and so on. And then the second thing is the prototype, and the third one is then we take a decision if we want to go for a real minimum viable product later on, or if maybe it could be also that it's not successful or the customers don't like it. So how long does a project like this take? And the answer was given in June in the kickoff meeting, because we said this kind of project takes 6 weeks. Because all projects take 6 weeks. Why? We do a time boxing. We cut the scope down that we could deliver within 6 weeks, a prototype. We are not focusing on the quality in the prototype. It's purely to create a prototype that allows us to take a better decision than spending 6 weeks on PowerPoints and drafting the requirements, and no one knows exactly if this is something that people would like. And after these 6 weeks, we decided, yes, the prototype was successful, it was connected, so let's go for some real further development. To be fast, you need to prepare a bit. So it's not about just saying we're starting from the scratch. What we did is that we developed a reference architecture that helps us to understand how we ingest data into our digital platform, how do we apply analytics for this data, and how to build a consumption layer for this kind of data at the end. And this is just visualized here in these 3 building blocks. I will not go into the details because that's most probably a bit boring. But what you see here is, this is the ingestion. From here to here, we ingest the data. That's just get the data into the data lake. Here is the creating insights, analyzing the data. to get really an understanding what we can do with this kind of data. And if we learned what we can do, we automate it and put it into this layer where we have the consumption layer. We transform the data for the consumption. If this is a dashboard, if this is an API, a native app, a web application, whatever we want to do. In reality, this is the ingestion layer. It's a pure serverless application or pure serverless setup. So we have the capability for single ingest, multi-body, or multi-file ingest. In this case, we didn't use the IoT layer because we need to grab the data or we need to cache the data on the device because these surgery tables are partly in areas you are not allowed to have a continuous connection to the cloud. So from time to time, we upload the data depending on the setup, where the surgical table is, and so on. So the data are coming in. We have Lambda functions, and we use step functions. At the end, the raw data will all be pushed into an S3, and then from there on, it will transformed into DynamoDB, which is also then a catalog for the raw data we have in. Then this is the data lake storage. So from there, we trigger as soon as we have new items in Lambda, we extract them, and we build a common data object out of this file. So everything ends up in S3. We use JSON here, and the JSON content is there. We are also schemaless in the data ingest. This means today we have whatever current, position, cycles as a data set we get. Tomorrow maybe we get temperature, we get force, we get whatever it is. It's just added. And we always extract the schema out of the ingested data. Why? Because this is exactly where we can apply any kind of big data analytic to this use case. And then down the road here is really going to the consumption layer. But let's look into the big data. What does big data or analytic really mean? This means that we have the raw data in an S3 bucket, and we don't know exactly for what we need for an individual use case. So what we are doing is that we can apply the services like Amazon Athena or machine learning directly, or spin up a Spark cluster to grab in the data directly from S3. Or in other use cases, maybe we use an EC2 instance, and we can put whatever we need on top of that. And the good stuff is quite a lot of analytical Amazon machine images are available. We can use just spin up. We will see in the second use case about analytics. And this is then the consumption layer I already mentioned. So we extract for this use case everything into a big SQL table where we can easily do dashboarding on top of that, just to create maps, geospatial information, where they end up, well, everything what we get from the smart product, from the smart actuator. And for sure, we have also here automatic analytic capabilities to push notification, to send out, to say, hey, there's something going on, there's a defect or there's a failure popping up. So that's an active information which could be consumed in an easy way. And that's more the dashboard for the OEMs. As I mentioned, this was delivered in 6 weeks, but based on some pre-built stuff and based on an understanding how we really build this kind of data ingestion, consumption, and analytic capabilities. Unfortunately, this is a new project. As I mentioned, we have this integrated, so something is going automatically here. But we don't have enough data to apply analytics. This is why I use another use case, data science. This use case is about car manufacturing setup. In this car manufacturing setup, it's just an example picture. I cannot put the right one in, but it shows so-called conductor rails. Here you have conductor rails, you have a car transportation system, and the conductor rails just is the power supply for these moving assets. The problem is we already do condition monitoring, vibration monitoring, and so on these systems, but there are problems with the conductor rails. Sometimes you have a problem with the conductor rails and then the complete system stops. And it's pretty hard to detect because you cannot detect it with vibration diagnostic because there's nothing vibrating if you have a defect there. The idea was that we put a high-resolution camera on top of the system and take continuously photos of the conductor rail. And this is exactly what we did. And this is one example of a photo. You see the green marked areas, they are all good, and you see the red one, and you have this small black point or dark gray point, and this is a defect. This is not a defect that leads to a stop, but this will, over time, lead to a stop if this defect becomes more critical. What we did is that I have in my team not only developers, I have also a data scientist in my team, so to directly build a complete solution, a complete prototype. And he applied data science technology, don't ask me all the details about that, to identify the defect. So that was pretty fast done, but the problem is you don't have only a straight conductor rail. You have conductor rails, you have slopes, you have curves, you have these transitions where you mount or connect two conductor rails together. And if you apply this analytics directly here to the different things, you end up in a mess, because then you always get a defect. So the accuracy is pretty bad. So what we want to do is we want to classify the images and that we only apply at the moment to the straight conductor rail images, this analytic. For the other, we need to, this is not done yet, we need to pre-process to adjust it in a way that we can again apply analytics to it. And for the transition, we don't need it at all, because for the transition, there is no problem, because it's just the connectivity, no problem in this, like this one I showed. How do you classify this kind of images? We decided that we use the MXNet, a pre-built Amazon machine image, spin up an EC2 instance with this image, and data scientists are playing around with data, but the most time they spend really on boring work, labeling data, cleansing of data, so that's not the funny stuff. So my data scientist, Lucas, had a good idea. He just said, hey, why should I label all the things, all the images? It's taking a long time. He labeled a bunch of images, and then he threw the image into a deep learning network, MXNet, and he tweaked it, and he get not a high accuracy, for sure, but he get a pretty good filter of the images. And then he just went through these images and said, correct, correct, not correct, correct, not correct. And this was much faster to label a huge amount of images, or an amount that is big enough for real training. And the second step was, he had more training, labeled training data, and he threw it again on a bigger instance and run it through, and the end was 99.9% accuracy. But that was the result. So now we have the classifier, we have the model, so that we only apply it to the right images. So what was the things we did? The images we get on a daily basis are 30 gigabytes. So we will not, Jan already mentioned it, we will not push all the data into the cloud, 30 gigabytes for one transportation system a day. And if you have a longer transportation system, maybe you have 60 gigabytes a day. So this means that we need to really do it on the edge later on. But we took these 30 gigabytes in an S3 bucket. We trained the model. We spin up EC2 instance using the AMI deep learner machine image with MXNet. So it was done like this. So my data scientist could focus purely on really tweaking the model and build the data science model. We started with a T2 medium EC2 instance for just exploring a bit, and later on he spun up a P2X large to really have the power for processing the huge amount of data. The complete classification was done in a few hours. because he only focused on using the setup and not really configuring 6-7 hours the technology stack. And then I asked, what was the money you spent for building this classification model? And then he said, I don't know. And then he calculated and said, around $1. If you look into the cost, it's 90 cents for 1 hour of an EC2 P2X large instance, 30 gigabytes on an S3. So it's really around $1 to just on the technology stack. So the cool stuff is he could focus purely on the data science. And you can build this in a few hours because you don't have to worry about the technology stack. And this is what we want to do in the data lake, so that we grab out the right technology that helps us to do the right things and create value instead of dealing with the technology. So next step, as I mentioned, is really deploying the MXNet model on an edge device. This will be then in January after Christmas time. Until now, we are doing some other tweakings in this project, but then in January, we really go for a prototype or for a real solution for the customer. So the complete project was again delivered in 6 weeks, but we had some spare time in between in the 6 weeks. Yeah. For sure, there's hardware also involved on which are doing colleagues in SKF, so it's not. But the data science part was delivered also in a 6 weeks approach. So thanks. That's from my side.
Yeah, so I hope you have seen quite a big spectrum what you can do, starting from just using Amazon Machine Learning as a developer, using different techniques to ingest the data to do prediction, and to use different techniques running on top of AWS to do machine learning and prediction. Okay. So thank you very much for this late session, and we both will stay here for a few questions if needed. Okay, thanks.
Thanks. Have a good day.